thank you everyone for joining. I will just make a short introduction and before to give the opportunity to Professor to do his presentation. Thank you for joining our webinar today. My name is Corentin. I'm a sales manager at PowerSys. So PowerSys is the leading provider of simulation software and services for electrification and grid. And we are supporting our customer in various domains like electromagnetics, power electronics, multiphysics, and system level simulation, CFD simulation, and finally power systems. So today, in today's webinar, we will discuss about permanent magnet machine technologies, topologies, and application. And to develop these topics, I'm very happy to welcome Professor Ziquang Zhu, who has an outstanding experience and currently leading many activities in the electric machine community, as you can see in this biography here. So Professor Zhu is the head of the Electrical Machine and Drive Research Group at the University of Sheffield in UK, the Royal Academy of Engineering, and Siemens Research Chair. He's also the academic director of Sheffield Siemens Gamesa Renewable Energy Research Center, the director of CRRC Electric Drive Technology Research Center, the director of MIDI Electrical Machines and Control System Research Centers. His currently major research interests include design and control of permanent magnet brushless machines and drive for applications ranging from electrified transportation through domestic appliance to renewable energy, on which he has published more than 1,200 papers, including more than 470 IEEE transaction IET proceedings paper. He is fellow of Royal Academy of Engineering in UK, a fellow of IEEE in the US, and a fellow of IET in UK. He recently has been recipient of the 2021 IEEE Nikola Tesla Award. So congratulations to you, Professor Zhu. And and also recipient of the 2019 IEEE Industry Application Society Outstanding Achievement Award. So today, so this webinar will last around 2 hours, okay? So the presentation from Professor Zhu should last around from 1 hour to 1.5 hours. And we will keep some time at the end to answer your question. So if you want to ask question to Professor Zhu, feel free to use the control panel of GoToWebinar application to write your question, or you can also interact with us using the chat system. And by the way, during the presentation, you will have the opportunity to interact with Professor Zhu by answering a question poll to check your knowledge about electric machines and the topic we will discuss today. So that's all for my introduction. I will now give, I think, no, Professor Zhu, you will be able to start sharing your screen. So I will make you presenter. Give me 1 minute. Okay. Okay, Professor Zhu, now you should be able to share your screen. We can see it.
My screen now?
Yes, we can see it.
Great. Well, thank you for your introduction. And first of all, I would like to thank JMAG and also PowerSys to invite me to give this presentation. And good morning, everybody in the world. And I hope the time difference doesn't make any difficult. Well, today I would like to share one of my presentations on electrical machine technologies, topologies, and applications. And first of all, I would like to introduce Sheffield. As you can see, Sheffield is somewhere here in the middle in England. And the University of Sheffield is a very good university. The engineering is always in the leading position in the UK. And Sheffield as a city itself is a very innovative city, because this is one of the origins for industrial evolution. And actually, the modern football clubs, two of them, and also for the football ground, they all started from Sheffield. One of them is nearby where I'm sitting here, only a few hundred meters away. And in fact, Sheffield is also very good for the students, because it's a relatively low living cost compared with London, for example. But we also have beautiful national Peak District Park adjacent to that. And in fact, my house is on the boundary, but still only 15 minutes drive during any traffic time to the city center where my office is located. So it's a very convenient city. And in fact, I've been at Sheffield for 33 years now. And so I'm one of the oldest Sheffield working in the University of Sheffield. And my group, Electrical Machines and Drives Research Group, is well known as a leading group globally on permanent magnet machines and drive systems. We have very strong industry collaborations, and as you can see there, we have 13 academic staff members and 8 professors among them. We also have very complementary technical skills. In fact, at the moment, we are interviewing for one new lecturer, and also we're going to recruit another professor as well. Overall, in terms of the PhD student number and postdoctor number together, we have around 100 personnel. So it is a larger group, and we, and in fact, our research activity spans all areas as a system, including power electronics and control, electrical machines, and energy storage. As I said, our group most well known for permanent magnet machines and drive systems, and we can make prototypes and demonstrators in the group, because we have all those prototyping facilities. And one of our features is we are very good at building the bridge between fundamental and applied research. That's why we have very strong industrial collaborations. Many of them, in fact, are in long term, and particularly in the automotive, renewable energy, aerospace, and the domestic appliances that market sectors. Include a lot of names here I put it down there, and you probably hear from time to time. And our group also hosts a lot of research centers. So here you can see we have 6 industrial directly funded research centers, and also 3 government-funded research hubs. These include Rolls-Royce, Siemens, Lomax, and CRC for the fast train, and also Métis Group for the domestic appliance. And we also have the EPSRC-funded Prosperity Partnership on offshore wind and the future electrical machine manufacturers, as well as other offshore renewable energy catapult-funded research center as well. I just very briefly summarize what I'm doing. So my research fields probably can categorize into 3 major areas. One is the one power. I'm the academic director of Sheffield Siemens Gamesa Renewable Energy Research Center, and also the domestic appliances. And I'm the adjunct director of Métis Research Center on Electrical Machines and the Drive Systems. And I put the S there because there's one at Sheffield, another one in Shanghai. For the electrified transportation, including electric vehicle, more electric aircraft, and also fast train propulsion, and some bit of ship propulsion, for example. And on the electric vehicle side, I work on the hybrid electric vehicle, full electric vehicle, mild hybrid, and the hub motor and the power steering in the area. Okay, and then for the aerospace, are also participating in the research activity with Rolls-Royce, and I'm also the director of fast train propulsion electric drives and the technology centers. Now let me start to talk about permanent magnet machines. As you all know, permanent magnet machines have the highest efficiency and also high torque and the power density. It's very interesting. It used to be considered as a machine which only suitable for some low power and probably not too bothered about the cost. For example, like aerospace kind of application, because it's relatively expensive. In fact, you can find those similar wording in Professor Tim Miller's book, and one of his earlier book, leather covered, published by Oxford University Press. This is a photo which I did the seminar together with Professor Tim Miller. You can see the JMAG seminar as well. And but here are listed some of them, and you can see the permanent magnet machine now very widely used in numerous market sectors. And also the power level now is at megawatt level. The highest power level I worked is nearly 40 megawatt, for example, for ship propulsion. And you can see the industry drives, automation, electrified transportation, wind power, domestic appliances. Here I just show you a couple of photos. This is a Nissan Leaf. I'm sitting in the car. In fact, all those photos are my photo anyway. And this is a high-speed vacuum cleaner, and my student designed this one. And this is a MIDI group washing machine, and I've been helping to develop the electric drive systems. And this is the Bosch's lawnmower, for example. And this is the Siemens one power generator. In fact, it is one of the first, earliest generators for offshore wind. But because this is the first, so we put on the onshore. And I was standing on the top. Something from here to there is about 100 meters. It's more than 100 meters. So I'm standing on the other side on the top. But it is safe, by the way. Anyway, and so it's a good experience working on the permanent magnet machines. At the Sheffield, we have already been working in that area for probably about 40 years. And so we have a very long track record on the permanent magnet machine. So today I'll focus on the essentially topology and some applications, and but mainly on the topologies, and then I will cover a little bit of the technologies. And during my presentation, I'll talk about the stator and the rotor topologies, and then focus on a kind of special machine with fractional slot number, and then talk about magnet gear, like a magnet geared machine, and also this fractional slot machine and the vernier permanent machine. But because of the time limit, and I probably wasn't able to talk about too much. But what I'll try to give to you is a picture. Essentially, I try to link all of them together. Essentially, I try to say most of the permanent magnet machines, they are in the same family. Even you talk about fractional slot machine, vernier machine, or magnet gear machine, they are all brother sisters in one family. That's the key point, the message I would like to give to you, okay? And then I'll show a couple of examples for electric vehicles towards the end. So, as I mentioned, I essentially would like to talk about a story of a magnet geared machine. Okay, sometimes people call it a flux modulation machine, air gap flux modulation machine. Honestly speaking, they are exactly the same concept. And even the machine topologies, they are the same as well. One is focused on the air gap field modulation. Another one is focused on the torque production. So just the two stages, because you know if in order to produce the torque, you first of all you need to have an air gap field. Any machine, if you would like to produce the torque, you must have the fields, two fields, yeah, with some frequency and the rotating direction, and also the pole number, for example. So in that sense, it's exactly the same. So that's why I'm saying is I'm going to talk about the frictional slot machine, Tavernier permanent magnet machine, and then why the magnet gear principle. Well, first of all, I don't know, and you know your background, and maybe some of you doesn't have too much experience on the electro machine. So I still like to start with the basic machine structure, permanent magnet machine. Okay, obviously, if we talk about permanent magnet machine, we must have permanent magnet. Usually they're on the rotor. It could be on the stator, but today I'm not going to talk about that stator PM type of machine. So mainly focus on rotor PM type of machine. And then in the permanent magnet machine, recently I have one interesting discussion with Professor Fred Easting. He said, I fully agree, by the way, you know, to produce torque in permanent machine, not necessarily we need to have two fields. We only need one field. And then another one is current. The current, we needed to have the copper to carry the current. So essentially it's based on BLI, Lorentz force principle. So for Lorentz force principle, we need to have B. Yeah, this B in the permanent magnet machine, mainly produced by the magnet. But then we need I. I is in the armature, on the stator in this case, in the conductor. So that's a current. But I don't need to have the current to produce the field. Of course, we have so-called armature reaction, but that's a different thing. Key point to produce the torque, I need B and I. But in order to improve the B magnetic circuit, I need I, the current, iron, needed iron. Now the iron is in the stator and also in the rotor, okay? So if you look at a basic permanent magnet machine, we only have three materials there. One is a permanent magnet, and the secondary is copper, and then the iron. So from these material, three basic materials, we can form a large number of machine topologies. That's what I'm going to show you afterwards. Here showing the examples of Toyota Prius, okay, and the hybrid electric vehicle, a V-shaped. In fact, this is closer here is exactly that one. And this is the I take this close session from my student report, because all my students, when they join me, they're going to start with analyze of Toyota Prius, because we got all the data for that. Okay, so I'm going to start with the stator side first, talk about copper. Okay, so the stator winding topologies, to be honest, not too many there. The first one at Sheffield, we call the overlapping winding. Why we call the overlapping winding? Because that's the end winding. You can see here, phase A, phase B, phase C, that's the end winding. So this end winding overlapped each other. Okay, so that's what we call the overlapping winding. So this type of winding topologies, and then normally you have relatively longer coil pitch, more than one slot pitch. And you can see here, from here, start from here, and then end here. But we call this distributed winding, and this one is concentrated winding. In fact, to be honest, there's a lot of people confused with the concentrated winding. I'll show you next one is also concentrated winding. Okay, concentrated winding, that means for each phase I only have one coil. It's not distributed. So that's concentrate. Okay, you can see from here is 1, 2, 3. Coil pitch is 3 slot pitches. Okay, so that is a concentrated winding because you only have one coil. But this one distributed because we have two coils there. Two coils there. You could have 3 or 4 more, depending on the slot number, pole number combination. So this type of winding is very popular in electric vehicle. It's the most popular one for electric vehicle. Why we would like to have this? Because by employ this type of winding, the coil pitch is almost equal to the pole pitch. Is almost equal to the pole pitch, and then you can utilize the so-called reluctance torque. The reluctance torque, because this reluctance torque is not relevant with the magnet. So in order to reduce the cost, reduce the amount of neodymium barrel magnet, which is probably the most expensive component in the machine, in the permanent machine, then you can utilize that. Then by utilizing the reluctance torque, then in order to produce the required resultant torque, and then you can reduce the amount of permanent magnet material. By the way, I would like to say, in terms of the torque capability, the so-called surface mounted magnet and interior permanent magnet machine, their torque is very, very similar. Depend on the design, of course. And this one we call the interior permanent magnet because the magnet is buried inside the rotor iron. This is a to the previous one. Okay, and you can see here the end winding here. Yeah, that's the end winding, and because they are overlapped, so they are usually relatively longer because when you try to wind it, you need to give the space for phase A and B, and so the end winding is relatively longer. Not only because that length from here to here is length, but also the end length. Okay, around the axial direction, the end winding tends to be longer. That will increase the machine size, and then consequently it can reduce the torque density if we're not careful. And of course, there's a trade-off between this type of winding topologies and also the reluctance torque, all that kind of thing there. Okay, and then another type we call it just as a pair. This one is non-overlapping winding. Non-overlapping winding. You can see here, I showed the two here, two typical ones. They are not overlapping. You can see the end winding. Okay, that's the phase A, B, C. And you can see they are isolated. The end winding doesn't have any overlap. And then this one got an alternate tooth wind, for example. And then they also don't have any overlap as well. So all these type of windings, we define as non-overlapping winding. And now, this non-overlapping winding usually are concentrated winding. Okay, they are concentrated winding, so it's not distributed. But it depends. You could have another type of like a distribution. Okay, and because in the machine, which I later will talk about it, and the coils belong to the same phase, may have some phase shift, then we still have some sort of distribution. Okay, but that's another matter. And otherwise, here is the concentrated winding. So you have concentrated winding for non-overlapping winding. You also have the concentrated winding for overlapping winding. Okay. And many years ago when I studied, I called it, this is all tooth wind, this is alternative tooth wind, and they borrowed the idea from the fault-tolerant machine. Then nowadays it's more popular. People call it, this is double layer winding, and this is a single layer winding. But I just would like to mention that the single layer winding is no problem there, but the double layer winding is very confusing with the conventional double layer winding, because the conventional double layer winding, you have the coil side, one on the top, one at the bottom. But this one, we have both two sides at in a side by side in the slot, side by side slot, rather than one up, one lower. Okay, this is also getting popular, and you can see this one, the coil very, very neat. And in fact, this one you can easily make the automation as well, make it modular, for example. But the problem is with this one, although the advantage is the winding is very neat and the end winding is very short, so that the machine is very compact, the couple loss is very low, but you can't utilize the reluctance torque effectively. Okay, so the reluctance torque will be reduced. It also, sometimes it depends on the slot number, pole number combination, could be even disappeared. This is why if you look at the electric vehicle, vast majority machines, they're not using this one actually, but using this one. Okay. I'll go a bit further anyway and talk about the
sorry
fractional
to
slot
interrupt
machine.
you, Professor Do, sorry to interrupt you. I think it's time for launching the first poll.
Okay.
Fine with you?
Yes.
And in the meantime, it seems that on your screen we cannot see the cursor of your mouse. So when you are showing something, we are not able to see. So maybe can you just try to unshare your screen and share it again? Maybe it will solve the issue.
I share my screen now.
In the meantime, I will start the poll. So to all the attendees, you will see on the screen the first question. Okay. Yeah, so now you should see the question. So you can answer the poll. We will let you a couple of seconds to answer it. So the question is why it is preferable to use IPM machine rather than surface mounted permanent magnet machines. Because of IPM machine use more magnets, produce more eddy current loss in the magnets, or have no additional magnets retaining. So you can answer the question, and we will review the answer in maybe later during the presentation.
Okay, shall I come back?
Okay, maybe Professor Zhu, let's wait a couple of seconds again to let people answer. It won't be long.
Interesting. I can't see your screen. I don't know
You
whether
can
the
see
audience can see
the
the screen.
question? Yes, because I'm seeing they are answering, so I'm sure they see the question.
That's good. That's good.
But maybe it's because you are sharing your screen.
Very simple question.
Okay, 10 seconds. Please answer now, and we will go back to the presentation. Okay, so I will close the poll right now. Thank you for all your answer. Okay, Professor Zhu, can you share your screen? Okay, I can see your screen now.
So in summary, I just try to talk about the frictional slot machine. Frictional slot machine is very simple. First of all, you can just define that the number of slots per pole per phase is frictional, it's not integer. I mean, traditionally it's integer, and this is a frictional number, and getting very, very popular over last 30 to 40 years. And although before that, you do find the frictional slot machine in the hydroelectric generators, for example, but least popular. And now is getting very popular. So this type of machines, essentially, you can have the short end winding and consequently high machine torque density and high efficiency. It usually can designed with sinusoidal back EMF waveform, and because the frictional slot number, and you can have low cooking torque, and then low torque level, and also showing potentially can have a good flux weakening and also fault tolerant capabilities as well. And as I said, it's now getting popular. One of the disadvantages I mentioned already is the reluctance torque may be reduced and or even diminished. So that's the problem. Okay. And now I'll talk about the story first. This is 12 15 slot 10 pole one. And essentially, if you look at the slot number and the pole number, it's 3 to 2. 3 to 2. Okay. Divided by 5, for example, in this one. That means K is 5 in this case. Then we have 3 and 2. 5 times 3 is 15. 5 times 2 is 10. Okay, so here NS is a slot number, 2P is a port number. So this used to be the most popular slot and the port number combinations for the fractional slot machine with non-overlapping winding. That means the coil simply just wound on each tooth. Yeah, they are not overlapping. And then in fact, this one has got a higher winding factor, because it has 0.866. But I put it down here, it's opposite. I put it down low winding factor. Yeah, usually 0.866 is not too bad, but I put that down as a low power factor, winding factor. The reason is I would like to make it even higher. Okay, that's a key point. So what I'm trying to do, I would like to maximize the winding flux linkage and also the power density. So why this one we only got the 0.866 is because the coil pitch is a short pitch there. Then it's lower. So in order to maximize the flux linkage and then maximize the torque and the power density, so I'm saying here is, can I make the coil pitch equal to the pole pitch? Yeah. If I make the coil pitch equal to pole pitch, then I can maximize the flux linkage. So obviously, we would always like to make some mathematical equation, right? And then here I put it on coil pitch equal to pole pitch. But this is exactly the same as this one. Okay, now let's have a look how we can achieve that. Obviously, we can employ overlapping winding, use the integer slot machine rather than the fractional slot machine. I'm talking about fractional slot machine, okay? But here, if we try to employ overlapping winding, make the coil pitch almost equal to the pole pitch, then I can maximize the flux linkage. You only make the short pitched winding and to reduce some harmonics. That's another matter. So essentially, it's this kind of category. But today, what I'm going to talk about is mainly not this type, but the other type, non-overlapping winding type. Okay, so that means I can't use this one. Otherwise, it's very simple. The solution is already there. Then it's very interesting. I just try to recall here. Long time ago, in fact, he was my very first PhD student at Sheffield, and we developed a very novel linear motor, which is tubular. This is a magnet, actually. This is armature coil, and you can move it along. Essentially, in principle, it's something like that. So we have one phase A is a tubular. The coil is a very simple, a toroidal one, and then another phase B there, and that's a real machine. Now, if you look here, the tooth here from here to there, so the tooth pitch from here to there is exactly the pole pitch. So we try to maximize the flux linkage. But then if you do like that, you have very, very big cogging force, yeah, cogging torque. But in linear motor, we call it cogging force. But how do we get rid of the cogging force? We utilize another phase, 90-degree shift. Then for the cogging force, the phase angle, it will be twice. So it's 180. So this one and that one, the cogging force are anti-phase. Get rid of it. So this is the machine we did a long time ago. Okay, so that's what we want to do, to make the tooth pitch equal to pole pitch rather than coil pitch, because the coil is just a toroidal one. Now, by utilizing this concept to this fractional slot machine, yeah, so we can try to do that as well. So we try to make the coil pitch equal to pole pitch exactly. Yeah, so that's the simple equation, to P equal to NS. Now this is the machine. We have 10 slot and 10 pole, okay? But you will find here, this machine actually is essentially got the 10 modulus there. They're all identical if you look here, 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 everywhere. The flux linkage definitely is maximized. But like I mentioned for the linear motor, you have very large cogging torque anyway here. But this is only one phase. That's a problem. If we want to have 3 phase, So this is not possible, except if you try to use 3 modulus like that, then it's, to be honest, it's not easy. And if you do like that, then you have actually you got the gap because of the end winding there. That's a problem. So what I try to say is this in theory is really not realistic machine. It will be very good if you want to use this one as a magnetic coupling because it's locked together. You can't have relative motion between stator and the rotor, but locked together as a coupling, that would be good. So that means we can't do that anyway. Yeah. So what do we try to do? We try to, I always call it one step back. Okay. So we make the difference, not 0, but as 1. So the slot number and the pole number only differ by 1. So that's very close, right? So we try to make the coil pitch and the pole pitch almost the same, almost the same. Then in this case, we can expect that the flux linkages will still relatively high. Yeah, so we can achieve high torque density. Because this is a fractional slot combination like that, usually the cooling torque will be quite small. Imagine if we want to make them differed by 1. So you can see I'm using 2p. That means pole number is always even number. North pole, south pole, they always come together. And then the slot number must be an odd number. Yeah, odd number in order to satisfy that. Then we can try to work out how many slot number, pole number combinations there. So we can find the 3, 2, and then 3, 4, and then 9, 8, 9, 10, all that kind of combination there. So you do have a lot of combination. In fact, you will find quite a lot of combination there. And then like a 3T is very popular. People use it for high speed application, for example. And then 9-8, you sometimes find people use it in the servo motors as well. But I'm going to show you some problem this type of machine. The unbalanced magnetic force could be significant. Depends on the electrical loading, how much current you put in. Okay, let's have a look. So this is an example of a 9-slot 8-pole machine. So you have 9 slots there, 8 pole there. What happened is in this type of machine is we have north source, all those there. That's like a conventional. But if you try to work out the best winding connection to maximize the flux linkage, it need to be like that. You have 1 coil here, 1 coil here, 1 coil there. That means the 3 coils should be adjacent to each other. Okay, so you have for phase A, you have 1 coil, 2 coil, 3 coil there. And also the middle one needed to have opposite polarity compared with the adjacent one. You can see here, positive, negative here, but the adjacent one here is negative, positive. If you look around the circumference, right, it's opposite. Then that one also the same. You have negative, positive that side. But to be honest, it's quite easy to think about. Suppose if you change here, then the current in that slot will be cancelled. And in this case, they all like a minor, yeah. So all the same direction, so that's fine. And they here all positive, it's fine. Yeah, so they all around that side. So we have all phase A winding here, B there, and then C there. So if you look at the open circuit field distribution, that means produced by the magnet. Yeah, you obviously first look at it, the field clearly seems like not very uniformly distributed. Okay, in the stator at least, you can see less flux line there, more here. But actually, if you look near the air gap, around this air gap, they are quite uniform actually, very cyclic, yeah, symmetrical there. So it's not a problem. The problem lies when you put the current there, no magnet here, no magnetic excitation, here only magnetic excitation, here only the coil excitation. So we have phase A and phase B excited there. Now you can see there, yeah, also not symmetrical circumferentially, but you can see here on the stator side, very easy. But the important thing is if you look at the field in the air gap, they are also not symmetrical. Now this is a problem. That means I have more flux here, less flux there. So consequently, you have a larger force that side to pull the rotor to that side. That's the unbalanced magnetic force. In reality, of course, it's the field always produced by the magnet, and then together with the field produced by the current, then it's something like that. Then you still have asymmetry there. Then you could say, why I should connect the coil like this? I can make it symmetrical, something like that. You're right. But in order to maximize the flux linkage, you must do that. Otherwise, the flux linkage is reduced. Here shows example. I'm not going to talk about that in detail, okay? And I'll show you a little bit there. You can see this is the well, star F slot or star F EMF phasor, and I usually teach during my lecture course. So essentially very simple. You first mark the slot number, and then you have 1, 2, 3, 4, 9 slot, 9 coil. So that's for each coil. You put it onto the tooth, okay? One coil, you mark. And this is a physically mechanical angle, okay? In this case there. And then because this is 8-pole one, so you try to time the pole pair number, which is 4. So if I fix that one there, okay, one there, then next one, 2, is 40 degree apart there. 40 times 4 is 160 degree. 160 degree. So electrically, where it goes? It goes here. 1 here, 2 there. Okay? 1 here, 2 there. Then you can apply to number 2, 3, 4, all of them. Then end up with the MMF or the EMF phasor diagram, and like this. And then you try to group them. When you try to group them, you should try to consider the angle between different vectors as close as possible. So that means the angle as close as possible. That's one. And the secondly, you can reverse the vector if you like. So in this case, for example, I can reverse the number 2 to here. Yeah, number 2 reverse to here. Then I can group 1, 2, 3 together. Yeah, 1, 2, 3 together. Is like this. Okay. And then that's why we got that kind of a coil connection. Yeah, like this one. This is how it comes. Okay. I'm not going to talk about that detail, although I'm going to show a bit more afterwards, but I'm going to escape that afterwards. Okay, you can always work out a lot that way. And then what we try to do is we try to analyze what's happening with the unbalanced magnetic force. So we try to put the current into 2 phase, for example. So this is in the brush DC operation. And another one is put the 3 phase sinusoidal current inside. Then we calculate the unbalanced magnetic force at any instant. What do you find is under the permanent magnet synchronous machine operation, that's I call it here is the brushless AC, and here is the brush DC. That means only 2 phases operate. So you can see here, the unbalanced magnetic force is that loci is a circle. The amplitude is constant. Amplitude is constant, but at one constant time instant, another time instant, they will change the angle, but the loci is circle. If you change the current level, then the radius here is increasing if you increase the current. Okay, it looks quite simple. But then if it's a 2-phase operation type, then we got a spider network there. It's quite interesting. And when the student initially showed me, I thought, that must be wrong. How can be like that? Such a nice one. And in fact, if you analyze, it's right, because here each point they all have the equal time interval or rotor position. Yeah. Then you can see there over here is like that. Then suddenly you have a jump. Suddenly have a jump. Why you have a jump? Is because you're switching the communication from AB conducting to BC conduction. You suddenly have a jump there. That's why it causes that. But in any case, it's similar things, like when the current is higher, then the unbalanced magnetic force is getting higher. In fact, I'm plotting here the amplitude against the current. It's all like that. It's almost linear. Yeah, almost linear. If you increase the current further, it will become non-linear anyway. But in the normal operation region, it's linear. Although it's not going through the 0, by the way, it's a bit tiny there, because that is due to the slotting effect. If you look here, You see, diametrically, I have one slot there, but there's no slot there. It's a tooth there. That also causing unbalanced magnetic force. But that actually only produces a very tiny bit compared with the one produced due to the current. It's very small. Please don't forget that in this case, it seems like a magnet is not playing. It's there. Okay, the magnet also important part is contributing. In fact, this unbalanced force is the value is field produced by magnet and plus the current field there together. Okay, there's another term there is which is the square of the field produced by the current only. Then that is a square relationship. That's why I'm saying if you increase the current further, it will be nonlinear. So this is the problem. Okay, got to unbalance my force. So what do? We step one step back, make that divided by t. Okay, and then the coil pitch and the slot pitch will be very close. I can show you this is quite a good one. Okay, I think because of the time, I probably need to talk a little bit less, more briefly. I notice the time passes very quickly. Now, for this one, when you divide by t, so you can have two scenarios. One is the slot number is higher than the pole number. Another one is the pole number higher than the slot number. So we have 4, 6, 8, 6, all that kind of thing there. This kind of phenomenon all happens. Even in the switch reluctance machine, you also can have that kind of switch reluctance. You have 6, 4, yeah, and then you can also have 6, 8 as well, something like that. Yeah, there's a permanent machine is the same here. And then you can find a 10, 12, 10, 12, 14. This is a popular combination, right? And so that's what we try to do. I did all this work in 2000, 20 years ago. Okay, and then you can find that the machine should be like this: 10 pole, 12 slot. Then end up with a coil connection. It should be like this because you have 12, 3 phase, so 4 coils per phase, and then you have 2 there and the 2 there. Yeah, here the polarity is also opposite. So essentially, if you look at the field produced by coil, it goes like that. And then there's another one there, diametrically, symmetrically allocated there. Okay, at least you wouldn't able to find the unbalanced magnetic force if the rotor is right in the center, not eccentric. Then it's balanced, no unbalanced magnetic force. You can see the field is diametrically is very symmetrical, and then you can work it out. I'm not going to talk about that further. Okay, you can work out why it should be connected like that. Very simple, and then you can see we can have the flux linkage with different slot number, pole number combinations, and you can see there, and for 10 pole, 10 slot one, I plotted there. Yeah, this one. It's not possible because that's only one phase, but I put it there because this is the maximum. Then you have 12, 10, 12, 15, and also that there. And then you look at the flux linkages, the EMF is like this. Okay, 10, 12, something there. 10, 15 is there. 10, 15 is there. Okay, the inside one. Unfortunately, I didn't show the fundamental here. Okay, but at least if you look at this, if this is operated as a brush DC, you can see the difference there. And then this is the line EMF because ultimately, if you have the torque is due to the line EMF, this got a lot of pseudo harmonics there. Okay, and then I just try to make a summary. It's a good machine. And first of all, slot pitch and the pole pitch is still very close. And then the winding is still non-overlapping winding, so the end one is very short. And still fractional slot number, you know, and so the cogging torque is still quite small. No unbalanced magnetic force. It's good. Now we can have a look further. So I mentioned that the concentrated winding, you can have all tooth wind, alternative tooth wind. So this is alternative tooth wind. At that time, what I got this idea is from the aerospace application because they're using this type, alternative tooth wind. Okay, so this one and that one, if we just try to make a comparison, they are very, very similar. This one, the end winding will be slightly longer. because used to be distributed into 2 coils, not only 1 coil, only 1 coil there. Okay, and but they are very similar result. You will see later. Okay, the coil just diametrically opposite like that, so symmetrical, no embarrassment force, and then you can work out that. That's a bit easy. Only have 2 coils there. They simply face A, B, C there. Okay, and then that's a machine. You can see there, this machine and that machine. We can share the same rotor. Okay, share the same rotor and the same lamination, for example, and then but we want the different. You can see that actually this should be a little bit longer than that, but a tiny bit there. Okay, so it's essentially a very good machine. Okay, I'm not going to talk about this further anyway. Okay, but you know, as a researcher, we're always eager to achieve better, even better performance. So because 12 slot 10 pole, still we can't achieve coil pitch to pole pitch. So what I'm doing here, I try to achieve coil pitch to pole pitch. How to do that? I try to make that tooth tip width the same as the pole pitch. Now in this case, because I put the coil here, yeah, then I need to make it that wider, another adjacent one narrower. It could be opposite, right? Depend on the slot number, pole number coming in, because this is a 12 slot 10 pole. If we talk about 12 slot 14 pole, then this one will need to be narrower, then adjustment will be wider. But the principle is the same. What do we try to do? We try to make the coil pitch equal to pole pitch to maximize the flux linkage. To max that flux linkage. You can see very easily here, this is the prototype there. It's a lot narrower here, wider here. So this from here to there is exactly the same as the pole pitch. Then we can collect all the flux produced by the magnet, maximize the flux linkage. Okay. And if you really want to work out the numerical, what are we doing? Essentially, we're like working out the coil pitch factor, winding factor, maximize it. Okay, so this is a bit just try to for illustration, and quite easy to understand that. Okay, now the machine looks all like that for different slot number, pole number combination. Okay, so for 4 pole 6 slot, it become like that, and then 12 slot 10 pole become like that when you make an unequal type. So clearly, when you try to use it in the low pole number, the difference a lot bigger. Here it begins diminishing. Okay, and then I have plotted the same thing a bit more there. What do you see? If you increase the pole number, slot number, and then the difference between this equal tools and the unequal tools type, they become smaller. When the pole number is smaller, then the difference is a lot bigger. Partially is because you can see the difference between the slot number and the pole number. The number itself is getting smaller and smaller. Here, they all divided by 2 anyway, but then divided by the pole number, its percentage is a lot smaller, so getting closer and closer. And then ultimately, because the leakage kind of things make it diminishing the difference. Okay, that's what I would like to say. And I will skip that and then talk about this all-tooth one, the alternative one, an equal one. So you can see all the machine there. As I said, this is all made by our group. We can build this in the group. And then you can see the interesting thing here is first we have to show the inductance. Okay, the self-inductance and also mutual inductance. You can see when you go from all-tooth one, alternative one, unequal one, the mutual inductance is reducing. Yeah, all-tooth one, the one you have the slot shared by 2 sides, but now they have separated by the middle tooth, so the mutual inductance is essentially gone. This is important because this is what the fault-tolerant machine requires. They don't want to have the mutual inductance. So in case one phase got problem, and it's not going to affect the adjacent phase. So no problem, no magnetic coupling. This is one. Another one is interesting. You can see that when you do like that, the self-inductance is increasing. Yeah, self-inductance is increasing. Now this is also important for the fault tolerant, because if this machine is surface mounted machine, so the inductance is quite small. So in this case, you can increase the inductance, then make the so-called per unit inductance to limit the short circuit current. So this is quite important. But on the other hand, this is also important, the inductance itself, because for the flux weakening, you used to consider the surface mounted magnet machine is not good for flux weakening. That's not true. You can achieve perfect flux weakening as well. That's not the problem with surface mounted magnet machine. By doing that, you can also increase the inductance to achieve infinite flux weakening capability, no problem. Yeah, surface mounted magnet machine, the problem is not lies here. So this is not problem. And then if you look at the cogging torque, obviously, and it's still quite small, but compare with the original 1210, it's increased, but still smaller than this 1510 time. Yeah, 1510 time. So I just talked a little bit. Then that's the EMF waveform. EMF waveform. You can see exactly like a calculated there, you know. I just duplicating the EMF, and then this is the line one, and then this is a measured. Okay, this is a measured one for 3 machine, unequal one, and all two swanned one, and alternative two swanned one. Okay. Now, most interesting thing is if we try to compare. Yeah, we try to compare 1010, 10 pole, 10 slot, and 10 pole, 12 slot. They almost identical. But here we have used the unequal two switch. Yeah. So this is what I say the dream comes true, because I want to maximize the flux linkage. So that's it. Then of course, if you can have a look at the torque, in this case is the brush DC operation, by the way. Okay. Then you can see the torque level is reduced and the torque is higher. Average torque is higher as well. Okay. I'm not bothered to talk about the agreement between the measure that doesn't matter. Anyway, the key point, if you look at the overall here, most the torque is higher. So this is the fractional slot machine. Okay. We can go further. Now in this case, I just mentioned that we have alternative two swans. Okay. Alternative, no coil there. Yeah. But we can also make that unequal, yeah, unequal by maximize the flux linkage. But this is the one people used in the aerospace for fault-tolerant machine. And in this case, you can see for fault-tolerant machine, the only difference here is they make the phase number even higher than 3. In this case, we have 1, 2, 3, 4, 5, 6 phase there, for example. Could be 5 phase or something like that. Now, important thing is, I'm sorry, the screen is not showing properly. Okay, this one essentially showing is when the phase A short circuited there, it's not going to affect anything, because from here you can see that flux, they all very localized, not coupling the adjacent coil, not penetrating into the magnet. So this is quite important. When the phase A got short circuit, is not going to affect the adjacent winding. So the adjacent winding, they still can operate. And also is not going to cause demagnetization, because the effect on the magnet is very little. Okay, so that's the whole thing. Now inside the key point, the torque is produced by the harmonics. Yeah, not the fundamental, not the so-called fundamental due to the coil. Anyway, it could be just a 2 pole, but here is a 1012 type, is a 5th harmonics, which is producing the torque. Now this is what the people called flux modulation or the magnetic gearing effect. Okay, I'm not talking about that in detail, but I will cover a bit later. Now for that kind of concept, we have a Rolls-Royce University Technology Center, and directed by my colleague, Professor Galanjo. Yeah, and this is all related with aircraft or aerospace. And because in the future, a large aircraft need to have 1 megawatt power, so it need to be produced on board. And this is a type of machine which you need to use with the fault tolerant capability. Okay, Of course, the packet doesn't need to be different, the type of magnet. You wouldn't able to use the neodymium ferromagnet because if you put the generator near the engine, it's very hot. So you can use the cement cobalt, for example. Yeah. And depend on the application, the market sector, the cost. If it's domestic appliances, cost is very sensitive. Automotive, yes, sensitive, but performance is also very important. And for the aircraft, the cost is the second consideration. The top consideration is the high power torque density and high reliability. Okay. And then we can do further with this alternative to SWAN. We can make it modular. So what here I'm doing is cut that into pieces. Okay. Split the tooth. Yeah. Make it modular. Because for some systems, you have very large diameter. And then you can't machine the lamination, cut the lamination into a single piece. You can't transport that. You can't assemble easily. So you need to make it modular. So this is also popular, okay, this type. For example, very often you use it in the one power generator, for example, because the direct drive has a very large diameter. So it's very slow rotating, and then the size is big. And so Sheffield, we have this Siemens Gamesa Renewable Energy Research Center here. I'm also the director for this. And in 2019, we have celebrated our 10 years anniversary for that. It has been very successful. And because we are developing the most reliable, high power density, high efficiency generators for offshore wind, we helped the Siemens Gamesa to become the global leading manufacturer for the offshore wind turbine. And we have helped the Siemens Gamesa to develop the 6 megawatt, 7 megawatt, 8 megawatt, 10 megawatt, and 14. I forgot to put the 14 megawatt wind turbine generators. And currently, we're also leading a larger government-funded project as well. Okay, and this is a photo that was taken when the center was established. At that time, simply called the Siemens One Power Research Center. And this is in 2019. Okay, have a nice cake. Okay, and it is a generator, but it's a cake. And this kind of modular topology is also very good for automation to reduce the cost. So I'm also the director for Meidi Group Motor and Control Systems Center. And in fact, last month was also 10 years anniversary. So this is a cake for 10 years as well. Okay, has been very successful. And that's a for example. We can go even further. That's all stator side. So when you look at that all-to-SWAN one, like a 1210 one, you can see we have 2 coils there. So obviously I'm thinking about, can I cut off here, cut off there? You can actually become like that. Yeah. The only problem is I analyzed all those and then I found that if we do like that, I needed to increase the back end a little bit. Okay. But then I thought, that's not very good. Because if you increase the back end, then that means the machine size is getting bigger. But then I'm thinking about, how about if we reverse it, we make it external rotor motor. This is the internal rotor motor. But if we make an external rotor motor, then I got plenty of space inside. So it's not going to waste any space, right? So it's not going to affect anything. Then, interesting enough, I look at the website, I found the one company, they're making that. It's exactly the same as I thought. Very often, sometimes you got independent thought, then somebody already done it before you, actually. So definitely they did it before me anyway. So it's called a Wave Class, a company called. And but then I look at it, I think it's very interesting. They have integrated the inverter and also that. So that is one module. You can see the gap is different here and there. That's one module. If you look carefully, you can see there one something like that. But unfortunately, when I look at it, they used it for the electrical vehicle, bicycle, the bicycle. Okay, then I thought, it seems a bit too much because bicycle is very cheap. That's the problem. And then you make it modular, performance may be slightly better, but the effort cost in the manufacturing is more. If you use just the integral lamination with the fractional slaughter, you still can achieve good performance. And there's loads there. In the electrical bicycle, vast majority is using the fractional slaughter machine. Okay, but unfortunately, a couple months later, I look at the website. The company like a club probably closed anyway. So I think it's important if you got a good technique, you must apply to find the appropriate application market sector. That's very important. Okay, so I'm going to talk a bit more now about the machine topologies, and I think I'm probably running out of a little bit time, I'm afraid. So this is a surface mounted one. Okay, and then you leave a gap, try to reduce the interpole leakage. But then you in the back end, you can also put a triangle hole there, a space. This is really interesting one. It can reduce the weight. Yeah, it can reduce the armature reaction. It can reduce the iron loss in the stator. You know, there's loads there anyway. It also can save the cost as well. Okay, I'll leave all those to you to think about. But I mentioned here, you leave a gap to reduce the leakage, interpole leakage. But I can equally do it, put a magnet there. So introduce the airspace and introduce a magnet is a good way to reduce the leakage. But meanwhile, if you put magnet there, you can also enhance the air gap field as well. Now I already put it here. Yeah, this is a hardback, right? Self-shading magnetization. The magnetization goes from outside by inside to come out again. So this is hardback. But if you look back, that is hardback as well. Yeah, that is also hardback. And hardback is good because the reason is you can self-shade, no back iron here even, no field, no leakage. Then all the field is this side, for example. Of course, you can put the back iron there to improve the performance if the magnet thickness is very small. If it's very thick, you don't need it. But if it's very thin, you still beneficial to put the back iron there. Another thing for this type of thing is you can have inherent sinusoidal air gap field distribution. So cooking torque is almost not there. Yeah, it will have a bit there if you have any imperfection, but otherwise it's not there. So you don't need to bother about this too much. Yeah, and you can have very high magnetic field, magnetic loading because the magnet you can see from here to there. So equivalent to the magnet thickness is from here to there. It's a very thick magnet there. Yeah, magnet thickness we're talking about around the magnetization direction. So it's very thick there. Okay, so it's quite good there. So the air gap field is good. So what's that mean? This is sinusoidal. It's a good property. Another one is large air gap field. So that means if I use that for application, I require large air gap. It's perfect. Or you even use it for complete air cold machine. For example, yeah, this is air cold machine. It's a generator developed by my colleague, Professor Quesadalla. No iron at all. Yeah, that's a halberd. That's just a coil. That's the cooling duct, for example. By doing that, it's a good thing is because some applications you need to have so-called idle state, no loss. That means open circuit or no load. We should have very high efficiency. If you have iron there, you have iron loss, but you don't have iron there, so it's very low idle loss. Yeah, only have a bit of AC copper loss. Then you can use the lead wire. In fact, this machine does use lead wire. This is used for the flywheel. Okay, flywheel. So that's a good application. Ironless machine. Another one I'm showing here is from is a prototype in Newcastle. We did a lot of machine like that as well, but I think I prefer use also other people's as well. Here you can see it's a fuel pump, but it's flooded. The rotor is flooded there. use the oil, and then you need to have the shell. So consequently, the air gap is very large, very large. So in this case, if you use the hardback machine, it's very, very good. It's very good, yeah, to produce the high air gap field, high magnetic loading, for example. And then you got loads of machine topology. Permanent magnet machine. I tried my best to collect a lot of topologies for the stator, okay? But even more is on the rotor. I'm never able to collect all the rotor topologies there. Here, just a couple of examples there. Yeah, you can have so-called inset, okay, consequent pole machine, and then interior type of machine. Yeah, this is all interior type of machine. And then you use the air gap to reduce the interpole leakage. You use the magnet to reduce the air gap, the interpole leakage. Yeah, you can utilize the flux focusing, for example. You can try to increase the reluctance, avoid the demagnetizing by bury a bit further and open that up. Yeah, compared to here. Increase the reluctance torque, for example. Utilize the flux focusing if you use 8-pole one. 4-pole is not showing significant, but when the 8-pole, 10-pole, like that, then you can have that. Yeah. And then this one, you got leakage there, then you need to put the air there, try to stop the leakage. But by putting a bit like that, then you can also reduce the armature reaction effect. Exactly like this. There's a loads thing you can tell. Yeah, I'm afraid I can't talk about that too much. Otherwise, it take me at least a half hour to 1 hour to talk about all those stuff. Okay, but I just want to show you there's a loads of topology there. And for example, even like this here, you have an arc magnet there, right? And then here is a flat one. Why are we doing like that? Because flat one is a lot cheaper. Manufacturing tolerance requirement is a lot lower. Then this type of application, maybe you only use it for ferrite or bonded one, bonded magnet, for example. That's okay. Otherwise, people tend to use this. Anything you talk about the performance, you need to bear in mind that the cost, no matter whatever you're using, application, and you need to consider the cost. Yeah, as I said, the cost only least sensitive for aerospace, and because the number is low and the manufacturing itself is important. As I said, the top considered in aerospace because it's the one is lighter, high power density, and then high reliability. Okay, then there's otherwise you always, no matter whether it's one power, automotive, domestic appliances, they all require low cost. Okay. Now here shows the topologies for the electric vehicle. Okay, you know the V shape and then delta shape, and also double V, and also double layer I bar there. This is employed by the Toyota Prius. This is employed by Nissan Leaf. This is by BMW, for example. Yeah. So they essentially all try to reduce amount of magnet by utilizing the reluctance torque. But meanwhile, they try to reduce the cost. The cost lies in the manufacturing of the lamination or magnet. The number of magnet segments need to be as low as possible. So for example, if you look at the number of magnets per pole, here only 2, here only 2, this is 3, this is 4. So the least the better. Okay. In theory, you can increase the performance by increase the layer number further, but you normally don't do that. Yeah, I have one example here. You can increase the further, but typically people only use 2 to 3. 3 is already very rare. Yeah, that's only people for try to write some paper probably. The company probably least interested. If you increase it to 4 or 5, for example, the performance improvement you bring into it is very small, but the cost of the material, the cost of the manufacturing increases very significant. To be honest, I've done a lot of work anyway for that, for the company. And the company will immediately turn down 4 layer. Oh, no, forget it. 5 layer. No, far too many. No, no more. Don't want it. And then, in fact, I asked a student to do the exercise for this Toyota Prius motor. They always can say, hey, Professor, I can improve the performance of that. when they improved it, the problem is they forgot the cost. Yeah, you can put the, obviously you can make it a two layer. The performance will be better than this one, but the cost of this one is cheaper than that. I know. So two this one is still very good design there. Okay, it all depends on how, from which aspect you look at it. So you need to be very careful. But the important thing, as I said, if you look at the commercial one, you can see they always use a very low number there. Yeah, 2. Yeah, of course you can try to use 1, but then from 1 to 2, the performance improvement is very significant. From 2 to 3, you still got an improvement, but probably the improvement is only half of that from 1 to 2. Then increase from 2 to 3, diminish it further. Then the return is quite small. Okay, that's quite important. And then here shows another one is like utilizing the flash focusing. So this is spoke type. In fact, this one is using ferrite. Okay, you can see the area here and also to the magnet cross-section area that was there. It's quite a significant difference there. So you can utilize the flash focusing, for example. So this is also very common as well. And of course, there's a lot of other topologies there, like X-field machine, for example. There's a lot. X-field machine tend to be popular as well. And but in any case, the manufacturing is more expensive, more difficult anyway. And it does have some companies try to make X-field machine, but you would say in the most of the applications, still laser field is more popular. And this one shows just a single air gap point. This one is double air gap type. Yeah, like a YASA type of motor. It's New York. This is toroidal type. Okay, double air. And this is a hybrid type. One side is a magnet, one side is a wonder field, for example. There's a lot of variety there. The problem lies for this X-field machine. One is the bearing. The bearing may have a large X-field force there. And more importantly, it's very difficult to make the lamination. I mean, YASA one is here. You can do the lamination for the stator core, but still can't do for the backend. Of course, you can say, oh yeah, I can make a soft magnetic composite, but then you have other issues like the maximum saturation flux linkages, flux density is limited, mechanically is very brittle, something like that, and there's a lot of other considerations there. So I just try to show you a bit more here. Okay.
Sorry, Professor Zhu, maybe we can have the second poll right now?
Yes.
It's okay for you?
I'll stop here. I'll stop sharing, okay?
Okay. So first, maybe we can have a look on the result of the first poll. So we'll share this. So you should see the answer on your screen. So I maybe remind you the question, why is it preferable to use IPM machine rather than surface-mounted permanent magnet machines? Because of IPM machines, answer 1, use more magnets. So 19% of the people answer this first possibility. The second one is because of IPM machines produce more eddy current loss in the magnets. So we have 23% of the answer on this one. And the last one is because of IPM machines have no additional magnet retaining. And 69% of the people answer this third options.
Very good.
So maybe, yes, Professor Zhou, you can comment and let us know the right answer.
Very good. Yeah.
Okay, so I guess the right answer was the third one, right?
Yeah.
Okay. So maybe now we can go to the next poll. And I will display the question now. So which of the following electric vehicle machines use 2 pieces of permanent magnets per pole? Is it the BMW i2, the Nissan Leaf, or the Toyota Prius 2017? So I think Professor Zhu.
2017, yeah.
Yeah, but no, we the people have to answer, but I guess
yeah. Well, as a
got...
year is important for that topology.
Okay, so you need to answer. We will let you a few seconds. Is it the BMW i2, the Nissan Leaf, or the Prius 2017 that use 2 pieces of permanent magnets per pole? Okay, 10 seconds left to give the answer. Okay, let's close the poll.
Okay, shall I share my screen again?
Yeah. So we will answer on a bit later, I think.
Yeah.
We'll give the answer a bit later.
Sorry,
So,
I noticed the time, and so I'm learning out a little bit, and I think we've started a bit late, and also got the questions there. And but it's good anyway. And so I will talk about this one very briefly, okay? And I think electron machine, the revolution still continues there, and I'm still talking about the fractional slot, the turning machine, and the magnetic gear. But so far, I only talk about the fractional slot machine and also the RPM machine, that kind of integer slot machine there. So I will very briefly talk about this, okay? And magnetic gear, okay? Now this is a magnetic gear which was invented by my colleague, Professor Kesatala, all right? It's in 2001. And essentially, the magnetic gear has 3 components there. One with a high pole number, low speed, another one with a low pole number, high speed, then got another separate iron pieces there, okay? And to modulate. All those 3 can freely rotating. But very often, I think you try to fix one of them. So 2 to rotating. You can fix any of them anyway, okay? And it's quite flexible. And then he also applied that concept into the machine. You can see here, that's a machine, because this is just a magnetic gear. And in fact, this is a prototype for that, very first one, okay? And I just would like to say, this is Dasen, okay? Dasen, that is me. And then that's someone here. And he's very interested in magnetic gear. He look around in our lab, everything, and then he most interested in that magnetic gear. He's always very interested in a lot of innovative ideas. But my colleague is really good. Case Dalek is very good, very innovative, and he got loads of ideas there, and even got a spin-off company from our group called the Magnetics, try to make it a commercialization. And then the concept that lies here, you can see from here, you can see the state lamination there, the rotor, like a magnet PM rotor is still there, but you can also see the magnetic gear there, that one there, right? And in fact, that outside one is stick with the stator. Yeah, then you got the rotor there as well. So this is a dual PM type of machine, dual PM type of, with a magnet on the stator and also the rotor. But in this case, you got one iron piece there also rotating. Okay, so this is essentially this type of machine. Now this is very, very important. This is a magnetic geared machine with a flux modulation. If you look at their paper, the flux modulation series is all there. Okay, and the important thing is because one side got a certain amount of pole number there, and then on the other side, the stator side, the rotor side, the pole number is different. The pole numbers are different. And then in theory, you can't produce a torque. But in this case, because you got the flux modulation there, because that flux modulation make that pole numbers on the stator side, on the rotor side, the same. That's a key point. So the torque production mechanism is still the pole number should be the same. A lot of people misleading others. Some papers they're saying, oh, a new theory invented. Now we can produce a torque with different pole number. That's wrong anyway, in my opinion. It is different there, but you have modulation there, make it the same. So still need to have the simple pair number, yeah, some rotation as well. So that's important, okay? And now, if we look a little bit further, this is magnetic gear. So essentially, you have a low pole number, high pole number modulation there. If you look at the pole pair number here, pole number there, and then pole pair number there. They must meet some sort of relationship there. Then from the low speed, high speed machine, you have a magnetic gear there. Okay, the gear ratio there. Then if you look at that rotational speed and also the torque, you will find the speed is the low speed. Okay, you compare with the low, you compare with others. That's if you use a high pole number there, then the rotating speed is reduced by the gear ratio, but the torque is amplified by the gear ratio. This is the gear. Okay. Now I'm talking about this. We have three components there. The magnetic gear need to have three gear. That's true. But the magnetic gearing effect doesn't matter. Doesn't matter how many you have. You can have even more than three, or less than three, two, for example. Because this is the key point of the magnetic gearing effect. Okay. And then the pole pair number, that kind of thing, is the flux modulation principle there. Yeah. So from here is the flux modulation. From here is the magnetic gearing effect. They are the same. Don't separate them. Okay. If you separate them, it's wrong. The whole principle should have flux modulation and with the magnetic gear. Okay, that's very, very important. And so that's why I'm saying Professor Kisela is very innovative. And this type of machine usually can produce a really high torque density. I've given a number there. Okay, it varies depending on which type of prototype you're making. Okay, sometimes the people say that, oh yeah, I can achieve how much, something there, but they don't give any result there, and it's difficult. But typically, it's a very, very high number. I think probably is very similar to the transverse flux machine. Okay, and like that. Now here I have a summary in 2014. I give a seminar there. So this is the magnetic gear. I try to link why the flux modulation magnetic gear is the two important parts of one of the theory and also application. This is there showing here. You can link the magnetic gear with the machine. Okay. So this machine essentially we have stationary modulating iron pieces there. So this iron pieces is stationary, but the PM rotors are rotating. They are rotating counter direction. Okay. And then from there, just remember, three-phase or multi-phase stator winding can produce a rotating field. So I can replace that, for example, in this case, the inner one by the stator like that. But I have A, B, C, three-phase. The field is rotating. This is exactly the same as this. Okay. No different. Apart from that magnet has been replaced by the AC coils. AC coils, three-phase AC. You can't have five-phase or more. Doesn't matter. The principle is the same. Now, this is the so-called harmonic magnetic geared machine. Now, for this machine, very interesting phenomenon there. Key point is a simplified version of this one, because this one got a two rotating. Now I only have one rotating. But the important thing, if you look at that, yeah, this iron is stationary, this stator is stationary, but you have a gap there. But that gap is really unnecessary. So you can remove that gap, become this. Simply by remove the gap here, it becomes. But this is a vernier machine. Yeah, it's exactly the vernier machine. At least one type of vernier machine. Okay. But compare here and here, the nice thing now. Here got two air gaps. Here only got one air gap. One air gap. Yeah. And one rotor, one stator. That's exactly the same. So that's what I'm trying to say. The flux modulation, the magnetic gearing effect here is the same. Here is the same. But then if we look another magnetic gear, we have one rotor, PM rotor fixed. Then the iron pieces is rotating. Another magnet rotor is also rotating. So two rotating. So here is, this is stationary. So I have another stationary one here. Yeah. That's the same, just a surface mounted. That's a spoke. It doesn't matter. Magnetic gear also got a topology with a spoke that part. This is proposed by my colleague at the Sheffield, but Peter in Aalborg, they have used the spoke type of them because of that. So I can put it there because it can utilize the space better. Here, the inside the stator space is limited, then utilizing this is better. Then outside rotating field produced by magnet replaced by the a stator again. This is a stator. So this is exactly the same as this one. No difference. No difference. Okay? Exactly the same. Now in this case, what do we have? We have one stator here, another stator here with a magnet. Yeah? Two stators. So we call the partition the stator. Of course, here I'm showing one extreme. Here all the state with the armature coil. Here is a magnet. You can split half, some bit here, some bit there. Doesn't matter. But this is the simplest one. Okay. And then the rotation part is only iron part here. This iron part you can also put magnet there. So anyway, that's not a problem. The key point is here. So this is the partitioned. I call the switch of the fractional machine. It looks like I got a two rotor there, but bear in mind, this is not rotor. This is a stator, stationary. This is stator, only one rotor, okay? But this rotor, we still got two air gaps there. We try to eliminate one of the gap, become like this. So what are we doing is we put the magnet into the stator here. Yeah, we remove the inner stator, combine the inner stator and the outer stator. We got the stator PM machine there. Then this is a sealant pole machine. Okay, they are the same. They are the same. They all form the magnetic gear. Excellent, isn't it? I did that in 2014 in October. When I got this picture, I was really excited. So research is quite interesting. Permanent mega machine, fantastic. Yeah, a lot of exciting things there. But I just would like to let you know, in fact, if you read my paper, you will find I did this first. I did publish a lot of paper on that first, and then I did that. And then I work on that. I'll do the reverse to it. Now I'm talking about the opposite way around. Okay. But in any case, all these type of machine, they are in the same family. They are based on magnetic gear and also flux modulation. Yeah. The basic, most important is here. Flux modulation, magnetic gear. Okay. They are the same. Vernier machine, switch flux machine, they are the same as well. Okay. They're all in the same family. I think that's quite interesting. Okay, now I try to go a bit further because I talked about the fractional slot machine early on. Okay, I would like to come back. So how about the fractional slot machine? Fractional slot machine is also a magnetic gear, also got flux modulation. Okay, they are. Let's have a look. Yeah, so I'm showing here a figure. I'm not showing in detail because otherwise it take too long anyway. This is the rotor pole number. I take that when the rotor pole number equal to the stator slot number as a division here, okay? Then you could have that, well, this is rotor pole number here, that slot number here, and then that there. And the key point here is integer slot distribute winding. So you have more slot number there, okay? And this is a frictional slot machine. So it's all around there. Then over that side is a vernier machine. What happened with the vernier machine? Vernier machine is the pole number is increased, okay? Is increased, is a lot higher. Now, if you look at that, we have done the analysis. My PhD student did a good work there. In the conventional that side, yeah, the PM torque, normal PM torque is somewhere there. But then when you go to that side, the magnetic gearing effect increases. Yeah, the friction sort of machine got the boost there. Yeah, in the vernier type of machine, magnetic gearing effect got a lot higher than the conventional one. So this is the one. I'm sorry, I'm only showing you the summary, not the detail, because the time limit. And in fact, we can look a bit further here. Now this is a conventional one. The pole number is less than slot number. This is the pole number higher than the slot number. It's more like a vernier type of machine. Vernier type of machine. This is more conventional fractional slot machine. Now, in that case, very important. What is doing that modulation everything? Where is the iron? Where is the iron in the where is the iron pieces in the magnetic gear? Yeah. Now, important thing is here. Sorry. Important thing is the slot opening. The slot, the permeance is modulating the flux. Okay, then produce the torque. In the conventional machine, the slot opening, the smaller the better, because you are not utilizing the magnetic gearing effect. You don't need to have the flux modulation. Yeah, then the conventional PM torque is higher there. But in the PM pole number higher than slot number, this type of vernier machine, the slot opening is important. You got the optimum area there. This is what I'm trying to show. Okay. This is the result from our numerical calculation analysis, and we analyze a lot of machine. Just to try to show you, vernier machine is a fractional slot type of machine. Okay, maybe multi-tooth type of fractional slot machine, maybe single tooth type, but it is still in the same family. Okay, and it's the same type of machine. And the only pity is when that pole number getting higher and higher, you got more and more leakage there, and then the power factor getting worse and worse. Okay, you can't gain everything. Unfortunately, that's the problem. Okay, so this is what I would like to say from that frictional slot machine and the vernier machine and the magnetic gear. I try to use just the graphically to show example, and then numerically you can read our papers, everything there. Okay. The
Okay,
final
Professor.
part. Oh yeah.
So sorry, again, short
Yes, yeah, take a
break
break. Yes, yeah.
to share the result on the last question.
Yeah.
Okay, so the question was, which of the following electric vehicle machine use two pieces of permanent magnets per pole? BMW i2 got 18% of answer. Nissan Leaf got 27% of answers, and Toyota Prius 2017 got 56% of answers. So maybe, Professor, do you want to give us the answer?
I think the answer is the BMW, is it?
Yes, I think so. So
Yeah.
yes, the BMW.
Here, that's why earlier I mentioned that the year is important, because Toyota Prius 2010, it is two pieces of magnet per pole, but 2017 got three there. Okay, so if
So
people choose the Toyota Prius, then they might in their mind that they're most thinking about the 2010 one. But
yeah.
in my question, I put it down is Toyota Prius 2017 one. Okay.
Okay, thank you. So the right answer was the BMW
Yes.
i2. Okay, let's go to the next question, which will be displayed now. So the question is, which of the following electrical machines is most frequently used in electric vehicle? Is it induction machine, permanent magnet machine, switched reluctance machine, or wound field machine? So you have a couple of seconds to answer.
We will review this one, the answer, I think, at the end of my presentation. Okay.
Yeah, sure. Okay, let's wait.
Okay, shall I switch back?
Please wait maybe 10 seconds. I will
Okay,
see
yes.
people are
Take
still
time.
thinking about the answer.
Yeah.
Okay,
I'm
10
sorry taking you a little
seconds.
bit longer than because we announced the total 2 hours, then my presentation will be 1.5 hours.
Yeah, I
So
think okay,
yeah.
but you have many interesting things to share, so it's thank you for that. Okay, so I close the poll. We will
Okay.
see the answer at the end, and Professor, you can share your screen again. Yeah.
You can see my screen, all right?
Yes, yes.
Well, the last part I'll talk very quickly anyway, and I also talk about the electric machines for electric vehicle. Okay, I think you probably will be very interested there anyway, and so it's a very high level as well. Okay, so for electric vehicle, this is a requirement. Normally, we would like have a high torque for starting to get off the street, quickly. We're all very young still. We want to drive the car, get a high acceleration very quickly. And then in the motorway, we want to drive fast. Yeah, so we need to have a high speed, but the high speed, you can't achieve it without the high power. Okay, so we need to have high power as well. Very wide range of this one, essentially. But currently, because the battery still have a little bit limiting the energy, and then we would like to have the high efficiency for the machine. And this region need to be as wide as possible. But please bear in mind that why I'm putting this wide range, put the arrow towards here, is because we want to have a low speed, light torque, light load, high efficiency. This is the most important. You get a high efficiency is not difficult. Any machine probably can achieve 95 almost anyway, with 1 point or 2 points something, a small region. But in order to achieve a high efficiency region at the light torque, light speed, that's not easy. Okay, so that's important. Of course, there's a lot of other requirement: low cost, low noise vibration, yeah, easy to manufacture, and all repair, even like, for example. That's another matter, okay? And that's a basic requirement. So I've been working with Toyota players for 21 years continuously now, and still working with them. And he is the first general manager I work with, and he retired a long time ago, and still got a good contact. I think he's the third general manager probably, and I'm working with another new manager. So they have changed the managers many times, 4 or 5 times already, but I'm continuously working with them. And this is when I was in Japan and give the presentation over there. I really enjoyed the visit. It's a fantastic company. And Toyota Group, by the way, is a very big company. So they have a lot of different divisions. My cooperation is mainly with Aishin Saki. Okay. And this shows the photo and my cooperation with Nissan. So I worked with Nissan continuously for 12 years as well, either direct project or by government. This shows 3 projects with the government. Okay. And I'm still working on. In fact, and this afternoon, I have my quarterly meeting with the board project. Okay, and but by the way, that's me. Okay, I was driving, and this is a Nissan engineer. Later he become my PhD. So now he already got his PhD. Okay, so we have very cooperating because the important thing that this is for electric vehicle, and the previous one is hybrid electric vehicle. The requirement is a bit different. Okay, and here what I'm trying to show you is take a Toyota Prius as an example. Okay, and then we try to design various machines to suit that specification and also with the same overall size. Yeah, machine length, egg length, stack length, everything. And so this is a type of machine. And particularly the slot number, we probably also keep it, and the port number, we also keep it as well. And so this is the requirement. I mean, this one you can look a lot of data on the website, and this is why we take this example, because some other machines, some bit of information is not on the website, or even I know, but it's confidential. I can't reveal it. Okay. Now this is the machine I'm going to compare. The first one is the induction machine with aluminum cage or copper cage. Then the second one is a synchronous reluctance machine. Synchronous reluctance machine. And then another one is a ferrite assisted machine. Okay, reluctance assisted by ferrite. Or reluctance machine assisted by the neodymium barium magnet. Then another one is a hybrid magnet with a neodymium barium magnet and also ferrite magnet together, mixed up there. And then last one is Toyota Prius. So this, I hope, covers almost all the materials, yeah, all the machine topologies, technologies. And you may find there's a couple of them missing. One is the wonder field machine, yeah, wonder field machine. But wonder field machine, I'm going to have a public seminar, and talk about that. And I think it's next month and also in December. And there's a talk there. But there's another one is a switch reluctance machine, which is not covered here. I personally don't believe, yeah, I strongly put my opinion very strong here. You can prove me wrong. I'm more than happy I'm wrong, okay? Switch reluctance mean there will never ever be a driving force for the electric vehicle, okay? But all the machines are here. As I said, otherwise only missing is one field machine. Now for all those machines, we have calculated the torque speed curve and also power speed curve as well as the power factor. Now first we look at the performance at the rated current. So you can see here, obviously, the PM machine definitely is the best in terms of torque. Yeah, you can see there, the highest is neodymium barrel magnet one. Okay, but the other machine is also not bad. Yeah, like even the hybrid one use a little bit of neodymium barrel, most of them ferrite one. They're very good there. Yeah. Okay, and in terms of torque, you'll find the induction machine is less. Yeah, in the induction machine, no matter whether it's aluminum or copper, so they are less here. Okay, but that's true. Normally, typically, it's about 20% less than the permanent magnet machine. Anyway, then the reluctance machine is the worst here. Of course, you can also try another way, or reduce air gap or something like that. But I'm not doing like that way, okay? Because if you reduce air gap, then your requirement for the bearing or this is getting higher. So the synchronous reluctance machine, it seems, is not so attractive for the application anyway here. And then you can also look at the power side. Also, the reluctance machine is also relatively poor. PM machine can achieve very nice, almost constant power there. Induction machine, it's good, but it's less. Okay, particularly high speed is reduced. Then all other machines are all achieving quite a good one. I mean, to be honest, you can all still further optimize it, but the journal conclusion will be very, very similar. Phenomena will be like similar. So that means under the related condition, yeah, PM machine is still the best. Yeah, induction machine is worse. Reluctance machine is worst. But if it's very interesting, if we look at the peak torque, at the peak current, we try to look at it. Now it's a very interesting phenomenon. The induction machine is the best. Now here, I think the current is more or less just twice, okay? Twice. Induction machine, you can go further. You can increase the current further for short peak torque. And then you'll find the induction machine is the best. It's better than the PM machine. This is quite astonishing because I used to always use the word permanent machine has the highest torque density and also the efficiency. I'm not saying like that way anymore because induction machine surprising got the highest. What that means? That means if you electric vehicle use induction machine, you can have a highest acceleration. That's very good. That's why Tesla, claimed that it's 100% true. Overload capability is very good for induction machine, not PM. PM will saturate. The worst because it's a reluctance machine. Even worse is a switch reluctance machine. It will be very bad for the overload capability. Yeah, because you need to compare rated and also the peak. Now in this case, that's an induction machine. Okay, the highest already shown there. PM machine still quite good because this is only talking about twice. If you use it 4 times, then induction is much better. The PM machine will be very saturated there. And then in terms of power also, yeah, in terms of power, it changes the position as well. Induction machine also become quite good now. Yeah, not as bad as here, and here is quite good. And in fact, here showing the machine we developed for the hybrid PM system will become the best. So there's a lot of like investigation today, optimizing it. But as I said, the journal conclusion is valid here. Then next one, I just let you have a look at that power factor. Okay, the power factor, the reluctance machine definitely is any machine, reluctance machine, no matter whether switch reluctance machine or synchronous reluctance machine, the power factor is not very good anyway. So here also showing the same here. Over the whole range, they're low. Others is not too bad. Even induction machine, yeah, here she seems as lower than the PM machine, but you need to look at the overall range. It's not too bad anyway. You know what I mean? Because even for the PM machine, it doesn't reduce here. So the worst part there, if you look at it, is also very similar. Yeah, but and no matter what happened, the PM machine, the power factor is always better. That's for sure. That's for sure. So this is a very brief comparison for a variety of machine. Okay, so it's a quite interesting one. And then obviously we need to have a look at the efficiency. Yeah. So if you look at the efficiency here, now that's what I meant early on. If you look at the maximum efficiency, they're all similar anyway. If we look at there's 93 there, 94 there, 94 there. The electron machine is not bad for that one. And then 95, 95, 95, 95. So it's all similar, just a 1% difference, not much. But importantly, if you look at that region is a problem. Yeah, the reluctance machine is quite narrow, very small. Definitely not as good as PM machine. PM machine, you can see 95 is very wide there. Yeah. And then the induction machine here, yeah, is 11. The induction machine, the efficiency definitely is lower overall. Yeah. Most importantly, you also need to look at the relatively low speed, light load. Here, PM motor is a lot better. That's important. This is a measured one, and we try to make it consistent. So this is also our calculated one. So you can see there, oh, good machine. Yeah, it's okay. And so that's efficient. Now, it's very difficult to judge how good this efficiency map there. So what I'm trying to do is to show you two examples. You take an NEDC driving cycle, yeah, and then look at that system efficiency. Okay, the overall efficiency. The number is here. What do you find is one conclusion. If you put the magnet there, then the system efficiency always very good. You can see more than 85. Yeah. Without magnet, it's only about 75. So more than 10%. More than 10%. That's a lot. You can see there. Yeah. All those machines, no matter whether it's firelight or a little bit of neodymium barium magnet or others, they're all very high efficiency, system efficiency. But the induction machine, yeah, synchronous machine, they are similar here. They are very low. Now this is a problem. Why? Because at the moment our battery still got a problem with the energy. Is okay. So that's the major reason. The conclusion from here is very, very obvious. PM machine is a current technology for electrical vehicle, not the induction machine, definitely not the electrical machine. The electrical machine is gone anyway. From those analyses, it should be eliminated. But then we can have a look at another type of driving cycle, okay? And it's just the torque and the requirement is a bit higher. You can see that this is at a very low torque and the low speed. Because when you drive, most of the frequented air is there anyway. But this one is a bit higher up there, okay? Then if you look at it, the difference become even bigger. Those with that magnet, I mean, the system efficiency, now they diverted, more diverted as well. But the important thing is this induction machine, no matter whether it's a copper cage or aluminum cage, and the reluctance machine become the worst here. Now here, the difference is more than 10%. A lot of them is nearly 20%. But this make a big difference. That means with the same battery, I can drive much longer distance anyway with the PM machine. Okay. So Tesla used to use the induction machine. It's a good machine, by the way. Okay, I'm not saying better machine. I already said showed that overload capability is really good. The efficiency is also not too bad. But with the current battery technology, then it's preferable to use the permanent magnet type of machine rather than induction machine. A lot of people worried about the resource of the neodymium magnet and also the fluctuation in the price. I don't worry. I don't worry. Why? Well, we have induction machine. We have induction machine. Still good machine. Yeah. And hopefully at that time we have better batteries. Then it's no problem. A lot of people try to work on magnetless machine. Yeah. And they try to develop a lot of new one. Our personal opinion is look at it. I think the performance is still not as good as induction machine. So we don't need to worry about too much. Anyway, worry about what we need to solve the problem rather than too far away the future. Is okay. And the induction machine is still good machine, but for the time being, it's definitely a permanent magnet machine. Okay. We still have a challenge even for permanent magnet machine, because if you look at that where you frequently operated is somewhere here or even here. Yeah, induction machine supposedly is good here, but PM machine no worse than that here anyway as well. It's also quite good there, but major difference is here. Most frequently operated region is here, but our machine, the highest efficiency is always there. We have a mismatch there. So we still have a lot today. To be honest, I don't have a solution. And if you have a good solution, you can bring that together. Set up a company, you'll be rich man. I'm quite sure. Yeah. And to finish, anyway, I just wanted to show you some summary here. PM machine got a high torque and power density, that's for sure. Not the highest, okay? Highest is still induction machine. And then high efficiency, that's for sure, highest efficiency. And then most widely used now for electric vehicles, no matter whether it's a BMW, Nissan, or Toyota, but even Tesla. Yeah. But the PM machine still got problem because it's a fixed PM excitation. So we could have so-called uncontrolled generator issues there. In case at the highest speed you lost the flux weakening control, then the induced voltage will be very high. That's a problem. Then another one is efficiency will be reduced at the high speed because you're doing the flux weakening. Okay, at the high speed. Magnet is always a constant one. But no matter whatever, PM machine is a current technology. If you don't believe me, this is a photo, Tesla. That's about 2 or 3 years ago when I attended the RCM conference in Greece. And Tesla has a boat there. And then I was looking for the induction machine. Then I found all of their machines the PM machine. I think they are right. They realized the shortages of induction machine for the time being. Anyway, okay. So that you can see I have a big smile there because I'm very happy. I'm permanent magnet man. Working on that type of machine. I can see in Tesla also using the permanent magnet machine. They are already using it as well now. So I think permanent magnet machines still have a lot of issues to solve, and it is very interesting. There's loads of topologies there, and I have very briefly talked about variety of technologies there and also some applications, but only very light. I think it's because of time limit. And so I'll stop here. And okay, thank you very much.
Thank you, Professor Zhu. Thank you very much. So I think we can review the last question before to go to the question part.
I'll stop my sharing. Yes.
Yes. So let's share the answer. So the question was, which of the following electrical machine is most frequently used in the electric vehicle? Induction machine got 10%, PM machine got 85%, and switch reluctance machine got 2%, same as one field machine, which got 2%. So do you want to give the right answer? But I think it's clear.
I think it's excellent, and the percentage also shows a little bit. I agree with 85% of people.
Okay,
Thank you very much.
good.
In fact, the percentage also showing is also very good indication what is the current commercial market, because the PM machine is the number one, and the induction machine is the second. And then others is relatively less. To be honest, you might hear a lot in the different presentations, or particularly with some companies, they specialize with one machine. They might emphasize that to be honest, recently I even see one of the on the website, one of the article title say that the switch relentless machine, the future for electric vehicle. Honestly speaking, I don't agree. Okay, if I'm wrong, I'm more than happy you prove me wrong. Okay, thank you.
Okay, thank you, Professor Zhu. So now we have some. We can take some minutes to attend this question maybe. So it's still time to ask question. We have maybe one question right now, but please feel free to ask more in the question tab or in the chat tab. So Professor Zhu, the question we have is the following. Why the power factor of the transverse machine is low and high cogging torque?
Transverse flux machine, okay. Low power factor, high cogging torque. First, I will talk about the cogging torque. Okay, the cogging torque, in the transverse flux machine, if you look at that type of machine, it's very interesting. It's exactly like in the fractional slot machine. I try to make that maximize the flux linkage. Then I mentioned that the coil pitch or tooth pitch equal to the pole pitch. And you can't directly apply to transverse flux machine, but the transverse flux machine essentially is that is tooth pitch equal to the coil pole pitch. When you got that kind of there, and then the cogging torque is always higher, because the cogging torque is due to the slotting factor and also the PM and the interacting together. Because they're integer, almost integer there. The transverse flux machine is one side of the core, start from north pole, then another side is south pole. So that's exact. Although it's perpendicular, but still the same. So that's why the torque level is higher. Of course, you have typically three phase, you have three module there, you have shifted it will cancel quite a lot out, but the residual was still high. In terms of the transverse flux machine power factor, first of all, I would like to make one point clearly. Transverse flux machine can have very high power factor. Okay. Unfortunately, at that time, the torque density is not high either. That's a problem. But transverse flux machine, the good thing is can have very high torque density. But unfortunately, when you have very high torque density, then the power factor is very low. That's a problem there. This is related with magnetic loading and also electrical loading. And you have a lot of leakage there for the PM. You also have a lot of leakage for the armature. Both is a both cause the problem. Then because you also have the high pole number there, because in order to increase that torque density. Now all those together then make the power factor inherently is bad. But as I said, that when we talk about transverse flux machine, we always talking about those machines with a high torque density with a high pole number. That's why the power factor is low. If you try to reduce the pole number and all that kind of thing, the power factor will get better and better as well. And that's the problem. And also another problem is if you reduce the torque density, then the power factor getting better. It will be very, very similar maybe to other conventional machine. And then you will find when the power factor is good, but then the torque density no better than the conventional one, but with added complexity in manufacturing. That's a problem. So that's why people not interested in high power factor and the low torque type of transverse flux machine. They only look for other type there. But I personally think it all depends on which application. Yeah, and if some application which is relatively small, low power, and then you not bother about the inverter because the inverter in any case will be oversized anyway. And then if you can utilize the torque density, that's still useful. And as I said, the key point for permanent machine, you need to find the best application for that type of topology. Okay.
Okay, thank you for your answer. Next question is, in a case of n minus 2p is equal to 2, the magnetic forces can lead to resonance with mode 2 of mechanical structure. Do you think this slot pole combination can be a good choice for automotive application?
So you're talking about that like a 10 pole 12 slot type divided by 2, and then you got like a vibration noise there, right? And, yes. So this type of machine, because the torque, for example, if we take a 10 pole 12 slot machine, and then their difference is 2, and then the if we talk about the harmonics as a fundamental, because that's the one produce the torque. So essentially is 5. Yeah, 5 is 10. 10 is 10 pole. So I'm talking about the field produced by the armature. And then this is like a torque production harmonic. And we can consider that as a fundamental. But unfortunately, in this type of machine, you also have a two-pole field there as well. Yeah, then that two-pole field is causing trouble because it will produce the radial force with the vibration mode order 2. So it will produce like elliptic deformation of the stator, then cause the vibration. Now, in general, I mean the noise vibration itself, this is not too high for 10, 12. You can apply in a lot of applications. I don't see too much problem there, but depends on the application again. Because the application, for example, if you apply to the power steering, it is a problem. Power steering company, they try to avoid using 1210. They more likely tend to apply this 3 to 2 that come commonly. That means multiple of 3 slots and a multiple of 2 pole, like that happen. Because over there, the vibration mode is a lot higher, and the stator is a lot stiffer, and then much lower. And so, as I said, it depends on the application. And if the application is for power steering, I suggest you not to use 1210. Okay, and then for normal application, for example, and also it's really covers a lot. I can't answer in very short time. For example, if this machine 1210, if you use the SPM, surface mounted machine, then it will be better than the RPM type. Because in the RPM type, the armature relation is a lot bigger. Yeah. And then because this all low harmonic is more related with the stator armature relation. So if the SPM machine, then the equivalent air gap is larger, then the armature relation is less, then it will be easier. So for 1210 is, in my personal opinion, it's not a problem for most of the application, and it is very, very widely used, and only needed to concern for some very specific application. Yeah, and also for some application, you're not using 1210, you probably is using multiple 1210. That means like a 2024. Then the vibration mode order will become 4, for example. And this is the exact same for 9.8. 9.8 is a fantastic machine, by the way, or 9.10. They're fantastic machine. Only when 9.8 to 9.10, the self got embarrassment force, that's the problem. But don't forget, 9.8, I can double it. For some application, I need a higher pole number. Then it's 1816. 1816 is an excellent combination. You know, there's no embarrassment force. There's a lot of applications that people are using that kind of idea, you know, multiple. And then the embarrassment force could be eliminated, or the vibration mode order can be increased, for example. So it's very difficult to always to say this combination is rubbish or something like that. It depends on application.
Okay, thank you. So
By
maybe
the
we
way,
have
another one I just try to add the 1210, for example. A lot of people try to work on that type of machine, try to reduce it. Then sometimes they try to properly design the frame, for example, then can reduce the vibration as well. Yeah. Yeah, sorry.
no problem, no problem. That's fine. So next question. How is going for concentrated winding limiting the reluctance torque in an IPM machine?
Oh, that's a challenge one. Because a tooth coil winding at itself is really not very friendly to the reluctance motor because the winding factor itself is poor for that. And but for the reluctance machine, I would like to comment. As I said, I don't have a solution, general solution there, but I just would like to comment because the machine we have a constant torque region, also constant power region. You will find in the constant power region, because over that side the torque is relatively small, then the percentage of reluctance torque is getting higher. You could find even in the conventional frictional slot machine maybe have 20-30% of reluctance torque there. Yeah, I just would like to comment on that. Okay.
Okay. Another one, how we model the hysteresis curve for memory machines.
How to model the hysteresis curve?
Yes,
I,
for
I
memory
think
machines.
I think probably better you need to read the paper. I think because I can't show it. It's a bit
Yeah,
complicated. There's quite a lot of model there. Now, what I would
yeah,
like to say is to model that kind of hysteresis kind of things there in the memory machine, probably the best way is if you try to store a range of curves like with a test result there. Yeah, because the key point is at a different demagnetization, then the curve will be different. So this kind of thing you can save stored there. And in terms of how to represent that demagnetizing curve, there's a lot of expressions there. Is okay. It's a good question because I didn't cover memory machine in my talk.
yeah, yeah. Right.
Yeah.
Next
Memory
one
machine
is,
is also
yeah,
memory machine is also another very interesting machine in my opinion. And the major challenge it lies it's because you need to magnetize it, demagnetize it. And the demagnetize is a bit easier. Magnetize it, you need to use minimum at twice of the rated current there. That's a problem there. Now the what I try to say is the important thing is you can use that one, but there's a lot of other issues there. For example, you keep doing like that. How about the winding insulation, for example? Yeah, how about the durability of the magnet property, for example? There's a lot of things that really need to take a long time of testing, and that's missing, I think, at the moment. That's in my opinion. And that's one. Another point is, man, machine, you don't need to do all the time. Yeah, you can use like a mechanical gear, only some stage, some, a couple of steps. Yeah, I still think it's a very interesting machine anyway. It's not yet at I think commercialized yet. I think, although I know Toshiba has a washing machine, but as far as I understand, in the Toshiba washing machine, the one they originally present is a fractional slot type actually as well, and then that flux adjustment is very very small, too small.
okay.
Yeah.
Maybe we have time for another question. Can we use single phase wound field for electric vehicle applications?
Single phase.
Yes.
Single phase one, the field one. I haven't heard about that one, but the multi-phase one, yes. Multi-phase one, the field machine. Continental is using that, and also recently I heard the BMW is also developing one the field machine. But one of the issue, apart from the conventional issue, is reduce the torque and reduce the efficiency. And the other part is relies about the rotor field excitation because you need to have the snippling and brush. And so this is one of the problem. And I believe Continental one is using that. And but BMW is using wireless power transmission and for the rotor side. And so for multi-phase one, yes, there's at least I'm aware there's 2 companies already using it. And single phase one, I'm sorry, I haven't heard about it yet.
Okay. Okay, so thank you very much, Professor Zhou. I think we can start because we are a bit running out of time, and we'd like to thank you very much for the time you spent with us today. I would like to
Thank you
remind
very
you.
much as well for Policies and also JMAC invited me
Welcome.
to give this webinar. And it's a pity I can't see all of you, and hopefully we will able to meet soon. And well, thank you very much for joining this webinar, and to all of you.
Thank you, Professor Zhou. So I remind to all the attendees that at the end of the webinar, you will have the possibility to give your feedback on the presentation and specify if you wish to have something, if you have more question, or if you want to know more about GMAG or power assist services, for instance. So we appreciated a lot your presence here. And of course, as Professor Zhou said, we hope to be able to organize some physical event in the future. And we hope that all of you are keeping well in the current situation. So thanks again for joining us today, and we hope to see you the next time.
Thank you.
Bye bye. Have a nice day.
Bye-bye. Bye.